All right. Hello, everyone. Welcome back to Gradient Descent, another episode. This is episode number 5. And with me, as always, is my colleague and partner of crime, Alex Thomas. He's the principal data scientist at WiseCube, and my name is Vishnu, and I'm the CTO of WiseCube as well. Glad to be here with you guys as well. And all right, so this week we're going to dive right in. It is a pretty meaty topic. For those of you, by the way, who don't know the podcast, we do deep dives on AI-related topics. We're both practitioners of AI for a long time, and so we love sort of discussing sort of the hot topics around AI and doing sort of in-depth discussions around those. So for this week's topic, we thought it would be a good idea to talk about LLM fine-tuning. This has been around for a while, ever since LLMs have, taken the main stage. People have been talking about fine tuning, but we thought it might be a good time to sort of revisit this topic because there has been a lot of recent advances in this area, and we thought maybe we could get a little in depth on it, see what the recent advances are, like what pros and cons, and get an overview of that. So, having said that, let's so Alex, this topic is, as I just sort of mentioned, fine tuning is around forever. I feel like, since the early days, I'm like year and a half now, or whenever the GPTs took sort of the world by storm. Fine tuning has been always discussed. OpenAI has offered it as a feature in their platform. And then there's been a lot of advancements around things like LoRa and other stuff that we've been hearing about. But let me, to set the stage here. So originally, when LLM sort of came out, GPT and whatnot, there was only sort of one kind of, maybe let's just step back. Like for the LLMs, there's the whole transformer architecture, and that sort of becomes the basis for the GPT itself. And then what was sort of unique about GPT itself was that they didn't just build a really powerful transformer and feed it the entire internet. They did something different. There was like a step two, and they took the transformer and they did something with reinforcement learning, right? And so we heard all about this RLHF, which stands for reinforcement learning based on human feedback. So let's just set the stage. What is it? What is RLHF for those, for those listening who don't really understand what it is, and maybe what is the classic sort of fine-tuning as we've come to know over the years? Can you sort of take us into that supervised fine-tuning, right? So
yeah, so I think if we sort of look at what the problem statement is, right? So with these language models, you're trying to produce the best, and I'm gonna use that vague now because it basically trying to make that not vague is what this process, all this is about. Trying to find the best language output, right? So, with just like a language model in isolation on its own, it's trying to find the most, when you're training a model on it, it's finding the most likely continuation of a text, right? It's finding the next step. So, if you think about this in terms of language, in terms of like hypothesis spaces, right? So machine learning, you have like what are this universe of possible answers to the problem we're trying to solve. The language model itself doesn't really find a specific answer, especially when we have such broad use cases like the LLMs or like general use cases. It finds like a much smaller sub universe of it. So the idea is like, now that it can produce valid output, a valid chain of tokens. So if I ask you, like, how's the weather today? You would say it's rainy. You could also say, you could say any valid sentence would be a technically correct response. It's just not semantically correct. It's not appropriate. So the language model, the training the transformer is learning about what are the likely tokens you are to see after a set of previous tokens. But this reinforcement learning is where you learn sort of how to pick from within that sub-universe. So you have the possibilities of like all language now. How do we pick the most appropriate response? So with reinforcement learning, it's treating that second level task as a policy question. Like, okay, so when I'm constructing my sentence, how do I get to a final output that's going to be the best by human judgment? That's the RLHF, right? And so we sort of start with what's called proximal policy optimization, which is where it's trying to learn that without changing the underlying distribution too much. Because you don't want to, like as you're learning these responses, you don't want to upset the transformer's ability to actually produce the most probable token. You need to balance those two aspects. But of course, policy learning and all that is extremely expensive.
Yeah, I just want to sort of intercept. I want to say, like, for those of you, I know reinforcement learning is all the rage now, and it's funny because before LLMs, I was actually interested in reinforcement learning for different reasons. But for those, so it is a very different branch of, let's call it AI, that was not in vogue for the longest time. It actually comes from this whole, control systems, that kind of branch of, like, Wolf and like, all of those, all those control systems scientists who've been working on this, and almost isolation, I want to say, right? It's kind of a left field thing. There's the Professor Sutton who was like up in Toronto, and he literally wrote the book on it. And for the longest time, nobody really, it was not mainstream, I should say, reinforcement learning, right? And the whole thing around reinforcement learning is like, hey, you're trying to learn a policy. Like, you're trying to learn what is the right next best action to take that can sort of optimize some sort, and then you set up a reward function, you set up a penalty function, and you set up the environment and almost like, hey, what is the next best action your system or your agent needs to take to sort of optimize like some sort of reward over time, right? And think almost like multi-arm bandit, right? Those kinds of things, which is where I think about, right, from where I was trying to learn reinforcement learning from. And then you're trying to learn a policy. So the policy would be like it could be a set of rules, it could be like a whole machine, its own model that, given a set of environmental variables, you as the agent decide to take one or a few actions that can then optimize or maximize your reward over time. And in this context of LLMs, the action that the agent or that you're training and the policy you're training for is, what is the output sequence from the transformer, that I should choose to maximize the reward that a human would give if they were to select, hey, which of these outputs, to your point, the weather question, would they rank the highest? And so if that was the reward, then you're trying to learn a policy that would maximize that human reward based on all of the potential outputs that the transformer model of the LLM spits out.
Yeah.
Right. Is that right? Accurate summarization?
Yeah, actually, and like you mentioned it, sort of like being like sort of in isolation from a lot of AI stuff for a long time, and that's because sort of like the machine learning, well, I think what probably most people would be more familiar with, branch, which sort of was like, okay, let's just think about like training relationships between variables. That sort of went off its own thing, but yeah, reinforcement learning doesn't really have that conceptual paradigm. It's not really thinking about like, oh, a fixed table of data sets and you're just learning relationships. It has this sort of space of actions, and it's learning how to take these actions. So in the previous episode, we were talking about DeepSeek's R1 model. They were doing this experiment where they were trying to rely much more on the reinforcement learning part than on the supervised fine-tuning. And the reason why, so the hypothesis they're going with is that that's how you learn generalization. Because if you are, let's say, just going off the transformer at every sort of token is going to produce a distribution over a set of tokens for the next token, right? So it'll say, like, oh, it's a 8% chance of being cat, 6% chance of being dog, 0.0001 chance of being, hyena. So
and just to stop you. So supervised fine-tuning, the difference once again between reinforcement learning and supervised learning, are we changing the layers of the transformer itself with additional data that's fine-tuned to the domain or the task at hand? Is that what's happening in supervised fine-tuning that's different than just say like reinforcement learning, which we're not changing any of the layers of the neural network of the transformer. We're just introducing a new thing in front of it. And so the original transformer model doesn't change at all, right, with RLHF. With supervised fine-tuning,
architectural approaches, with some of the reinforcement learning stuff, you do update the parameters in the model.
We do, okay.
So there's sort of like two ways of doing it. One is you can learn like the policy model, as you said, as layers on top of it. You can also basically learn the policy model in the layers of the existing transformer, right?
I see. And supervised fine-tuning is always going to change the layers. Is that it, or is there?
Yes. Okay. Now, of course, again, that's sort of like this terms of asterisks. There are clever ways of like maybe you only change part of the architecture or something like that, or you can add things on top of it. That's sort of like the whole, or you have like these models that act as layers on top of like a LoRa model or something like that. But like fundamentally, the difference that you learn your transformer, and that learns like the statistics of these sequences, and then the things you do afterwards. Like for example, in the DeepSeek R1 paper, they mentioned how even they weren't able to do anything. They had a problem if they didn't do any supervised fine-tuning because it would not learn formats correctly. And I think that's likely because maybe the human feedback on formatting is probably going to be a lot less informative.
Precise. Yeah,
a lot more precise. Because it's really sort of a deterministic question. And that sort of also relates to like another thing we'll talk about later on.
Is that the main difference? Like, talk to me about what, like at a high level, what are the downsides of just doing RLHF? Is there like
the problem the DeepSeek team said is that when they did that, so they built a transformer model and then they just did RLHF, no supervised fine-tuning. It would return sometimes with it would like ignore specific format requests, but also it would return stuff in a mix of English and Chinese. Because those are the two main languages they were working with. So it was returning stuff that was like correct and did match with the various human feedback, but it didn't learn. So like, if you got into a space where it was saying like, oh, the ultimate move at this point is to switch from English to Chinese, it would do that, even though that actual transition in like the action space should be extremely rare. For some reason, just relying on reinforcement learning did not learn that was right, or did not learn it enough. And there's probably lots of things we can conjecture as to why it would do that, but yeah. So essentially, what they did is that they did a small amount of supervised fine-tuning so it could learn formats and stay consistent with language output, and that seemed to be what brought them like on par with.
But in terms of computational capacity, obviously, DeepSeek, that's why everyone's speaking about it. Like at least the hypothesis is like, hey, we can do this with much less cost compared to previous versions of even training the model. But like, is there a computational complexity cost difference between SFT and RLHF?
Yeah, and I would say like it's you're someone who's like spent a good amount of time learning about reinforcement learning. It can be computationally very expensive. Now that being said, the DeepSeek team is like, hey, this is about generalization, and there's many ways to achieve the reinforcement learning. There's many ways to like learn the values and learn the policies. And that's sort of like one of the things we talk about like for this podcast, which is we have sort of like the traditional RLHF, but then there's other ways of learning the policies. There's so there's that's probably the more common way, or I'll just say traditional way of learning RLHF for LLMs is proximal preference optimization. So that's where you are learning pairwise preferences. So like, which response is preferred by the people. Now, that's of course a very good one, because if you're doing sort of like the more like traditional, just like learning a neural network to learn the Bellman equation and stuff like that, if you're doing that, you end up having to get a large amount of precise human data. So you have to have humans give scores, and as soon as humans are giving scores, it gets really messy. Humans aren't good at that. At least that's just humans' opinion. So we move to the pairwise thing. Pairwise is much easier to gather human data on. But again, still with PPO, that can still be computationally quite expensive to do. So then came the development of DPO, so direct preference learning. So that's using the, I forget the name, it was something Terry formulation. Basically where they turn the preference thing into the expression of the preference and the formula into a probability. It's the I cannot remember the name of that.
And so is this an optimization
Bradley
that you're
Terry. Yeah. So that's the DPO, direct preference optimization. The Bradley Terry methodology. So that turns the expression into a probability, and that lets you do some other like clever math tricks and make it computationally much more efficient. Now,
and so this was considered a sort of an optimization to doing RLHF, which is obviously could be computationally more intensive. And what were the results of like DPO? I know I've heard of DPO a lot of late as an alternative to RLHF. By the claim, of course, as you mentioned, simplifies the fine-tuning process without the separate reward model we talked about with RLHF. Like, you got to come up with this reward model, and you got to train a policy, and blah blah blah, all of this stuff that you have to do with RLHF. You're saying this simplifies all of that.
Yeah.
And how were the results? Does it work? Are people just using this now instead of RLHF all the time, or what's happening?
Well, for a while, everyone's moving to that, and like whenever you have sort of like in any sort of like AI machine learning problem, when you haven't, when you got to the point where you haven't sort of like maximized the use of data, anything that lets you train more, like an optimization in terms of speed, will let you improve your performance as well. Because like, instead of like leaving this model to train for like 5 days, I can achieve a lot more training in those 5 days. And so you got performance improvements for that. Now, it was interesting. Is like there was a discovery of a bit of a problem with DPO, but what I find interesting about it is that the problem was observed and then mathematically discovered.
Proven. Okay. So it was observed sort of. Yeah. Empirically before it was proven out mathematically.
Yeah. And because there was this problem where that people noticed that sometimes it would lead to like for certain tasks when you were learning it, it could lead to very bad results. Like it would just learn a very wrong input, or like more specifically, this is where they got to the math part of it, is that if let's say you were learning a task, and again let's go back to sort of like hypothesis space thought of it, and we have a small universe of possible answers or responses to that task. Excuse me, but your data was very deterministic. The scores were very extreme. But you didn't want it to rule out certain things. You didn't want it to be too aggressive at updating, right? Because that's one of the things that's going on with DPO, because you have two terms. One, you're learning to optimize sort of this preference expression that they did with the Bradley-Terry formula. And then the other part of the regularization term is using KL divergence. So basically making sure that the distribution of tokens that's coming out of the model does not change too much. But what they found is that for certain problems that are very deterministic, the regularization was not strong enough, it didn't work. And no matter how much you set that regularization term, it would eventually get overwhelmed. So essentially, if you had a problem that was in the Google DeepMind paper, they use examples of like when the grade that's coming out for the preference between the two things is less than 0.9 or above 0.1, everything was fine. Once you moved into the most extreme sort of 20%, the model had a tendency to just go towards extreme answers. So if you had a thing where like the answers were too deterministic, then the model would be too risk averse. It would just learn that, okay, we'll never try that thing. And you don't want to do that. You want to leave it open because otherwise you lose generalizability.
Right.
So other methods have come up since then. It looks to me like there's not sort of like a community consensus on the new method. DeepMind proposed their thing called IPO, where they're trying to, from what I understand, it loses some of the computational benefits of DPL, but not too much. But it preserves the point that the pairwise comparison. They're essentially, they've proved that this occurs with DPO. The hypothesis, sort of like conceptually about why it's going on, is that when you go from the pairwise to the pointwise, which is essentially what DPO is doing, evaluation, that's where this problem is occurring. Now, IPO is supposed to preserve the pairwise information, and so should avoid this. There's another one that came out. I've just been reading something called KTO, where they're involved in this economic theory, trying to take into account the risk averseness aspect. So it looks like the community's sort of still searching for like what's going to be the new hotness on the matter.
Right.
Yeah.
And yeah, this it's fascinating because this is we're talking about, this is stuff that's literally in the cutting edge of like research here, because it definitely doesn't seem like the research has settled on sort of the optimal answer here, or even something that's going to work pretty well for everyone around. So speaking of which, what are people doing? What are some of the real world applications? Like some of the probably the frontier models that are coming out. What are they doing? Like, are they using RLHF still? Are they like adopting DPO? Are they waiting for the next like version of like a better improved DPO? Like what's happening there?
Well, I know like maybe this is exactly like the latest models are like a year old, which is like ancient history now. Like Llama 3 was trained using DPO, so like there's not been a lot of time. I know that some Gemini models, they're using IPO for that now, for doing their for learning the human preferences. KTO was from let's see.
I've also heard Mistral also used at least one of their versions adopted DPO. Looks like yeah, and so people are using DPO.
Yes. And like it's not bad. It's just like it has these corner cases where it doesn't work. So I would say like if someone is, let's say, trying to decide now, I would say you could use DPO. It's not like a complete fail if you use it. Just like keep in mind those limitations. I'm curious to find out like what are sort of like the next steps. I don't know if it's out what LLaMA.
It looks like even P3 or Phi3 also uses DPO for its optimization, which is obviously not an LLM, but still a language model, but it's a small one, which we're all fans of, at least here in the show. So it's definitely being used by some of the frontier models.
And it looks like LLaMA 4 also used DPO. So like it's still being used. Like the problem is there, and research is being found that like find out what's this next step. But like that shouldn't be taken to say it's like, oh, DPO is like terrible. It's just in certain issues it runs into that. So yeah, I think like people should probably like keep an eye on like what's coming out of some of the big teams that are doing this. and if you are training a foundational model that's maybe more like targeted to your domain, if you're like building a foundational model, personally, I would recommend going with something that's a little bit more established. So maybe stick with DPO for right now, because look what happened when we switched to DPO. You got this cost increase, but it introduced this issue that it took a while to find. So I would say if you are more concerned with building like a reliable foundation model for yourself, stick with something that's a little more understood, even if it does have weaknesses. And I'm sure we'll probably figure out with Google pushing for IPO, KTO seems to be popular in some online communities and all that. We'll probably learn about what might come next. Soon.
Right, and just to, we should clarify here once again. There's two main ways of fine-tuning in general. Fine-tuning is such a broad word, but there's supervised fine-tuning methods, which literally go and change the parameters of the underlying transformer model, and that's where things like LoRa, right, those things do that, and whatnot. But then there's alignment techniques, right? What DPO and RLHF and all of these things they do is try to align human preference to what the model outputs were, using some sort of a secondary data set that usually is much smaller than the original data set that the transform model was actually trained on. Right.
And it is about alignment with human preferences. So conceptually, most of the time you're not thinking of a deterministic problem. You're thinking of something that's much fuzzier. So maybe if again you're training your foundational model and you want to learn have some tasks on it, maybe try to identify the ones that are too deterministic, and instead of doing you using your DPO train to do it, maybe just do some supervised fine-tuning for those tasks. That's right. That's probably a good choice.
Yeah, because I should say there's all these techniques, right? But whenever we think about personalization of LLMs to a specific domain or specific task, there's so many levels of this that all require various levels of effort, if you will. All the way from hey, we talked about prompt engineering and few shot prompting and prompt optimization and things like that, which is the low cost, the things you should try well before you think about fine tuning or alignment or preference alignment or any of those things, right? Hey, just stay at the prompt level, try to optimize your prompt, use few shot examples, use techniques like RAG, and try to see how much you can actually, what kinds of results you're able to get with those without changing anything on the underlying foundation model.
Yeah.
Right. Once you've sort of exhausted those techniques and you've sort of plateaued, if you will, on the kinds of results you're seeing, typically then is when you have to start thinking about fine-tuning in general, right? You're okay, to your point, maybe you start thinking about supervised fine-tuning. And by the way, OpenAI has made it so easy, right? They even have a UI. You can literally upload a bunch of examples, and then they would just fine-tune. And they don't really talk about what techniques they use under the hood. And so whatever fine-tuning techniques they use, we don't know if they use DPO, we don't know if they use LoRa or something else. They build a fine-tuned model for you based on the examples they've uploaded, right? And that does usually, depending on the data you provided, it might actually be enough. It might actually give you the boost that you need that's good enough for your problem at hand and for your domain and task. Of course, and then if that doesn't work, right, then you go on to things hey, maybe you want to consider RLHF, right? Maybe you want to do your own fine-tuning on top of it, or preference alignment and things like that, so you're trying to squeeze more performance out of the underlying LLM itself, or some open source or foundational model that you're building, right? Is that how do you think about this whole person space, or what do you think?
Yeah, definitely. Yeah, that's what you said. You start with the prompt engineering, few shot, RAG, maybe even if you, depending on what kind of problem is, if it's something where you're trying to build an agent that does multiple tasks, there's also hey, are any of these tasks ones that I could solve using a classical model, that I might be able to control a little more easy. And like I said, supervised fine tuning is made so easy now. Like I would, compared to like a year and a half ago or something like that, I would probably, move that up the priority list. Like, oh, that's actually pretty easy to do now. So if like your choices in between, having to gather a bunch of human data in order to do few shot, versus like maybe fine tuning on a related problem. Because here's the benefit of supervised fine tuning. It's like you can do supervised fine tuning on a similar problem and probably get some benefit from the transfer. If you are doing few shot, you need to be doing your problem. Like it can't be like near; it needs to be your problem. So like I would say that depending on your task, I agree with you. Sort of like your order of operations there.
And by the way, one thing I should call out, like this is something you've done a lot, is be able to take a complex task and sort of break it down into smaller modular tasks. Which most people, like when they're starting out, they're always thinking like, I want to do this massively complex thing. And of course, your foundation model, it doesn't do as well as you thought it would.
Yeah.
Right. And then we've experienced where we've actually, you've written a paper on this whole thing about how breaking down a really complex task into multiple smaller tasks actually improves the accuracy without doing any fine tuning at all. Right. Do you want to quickly talk about that?
Yeah. I think that's a great point right now because this one way maybe to think of it makes it easier is what's the information content of your problem, right? So you want to be able to give it some information and you want to be able to generate some information back. If you can do part of that problem, let's say outside the LLM, maybe with rules or maybe with like a simpler classical model, that means that it's easier, there's less for the LLM to do. And so again, as we're talking about the searching this hypothesis space, to go back to this thing from earlier, what you're doing is you're massively reducing the hypothesis space you're working in. So the more things you can pull away from having to give into like a single prompt or something like that, the more efficient it'll be. And also, even if breaking it down, you're like, oh, I still need an LLM for all these parts of it, that's fine. Likely, you're not even going to incur a cost increase. Well, because think about it. If you have a problem that requires, let's say, 4 steps, but you give as a sort of like a chain of thought style prompt to an LLM, and to do that, you're giving all these same inputs for it. Well, if you broke it up into 4 different prompts, you're still paying the same cost, right? You're still getting like these same inputs, outputs, because you're paying by the token. So even if you break it up, it's going to be better, even if you're still using the LLM for all the parts, all 4 parts of your task. Because again, if you think of like what's the hypothesis space of a response to that one big prompt, that's very, very huge, right? So for that, it's basically the Cartesian product of the answer of the hypothesis space for the 4 individual problems. Yeah. And breaking up has another benefit of you can potentially use the results of one to narrow down or improve the prompt.
Give it more context for the chain. Yes. Yes. By the way, some of these steps in the chain might turn out to be not requiring LLMs. So we've noticed this. Like, hey, this is just just need embeddings to solve this and do a cosine similarity or something. And now you've reduced the cost of the overall number of tokens you're paying for and all that too. And you've narrowed down the problem scope itself, which means that even if you decide to do fine-tuning for some of these steps or alignment, the amount of data that you have to go collect, data, is also going to be less, right? Yeah. And so, anyway, I think this is all obvious to us. Like for people who've like worked with classical sort of traditional machine learning space, you sort of think about a complex pipeline like this and trying to break it up and make it modular. And like, I think we've been spoiled for choice. Like it's like, hey, everything is just throw everything into the LLM as like a 1-shot or a few shot prompt, and then it'll just spit out the answer magically, and it will, but maybe not all the time. It's going to meet your bar for like what's good enough for your problem domain or your task.
Yeah.
Right. And that's when you have to. Yeah. Go ahead. Sorry.
I want to make like a special note to some of our brave, less technical users. because one of the things I've noticed is that less technical people who are doing this, they can do a lot now with LLMs. Because one of the first things you learn when you take a coding class is breaking down problems. The classic thing of like, write down all the steps to brush your teeth, right? That sort of classic problem. And non-technical people often haven't received that training. I would say, try and exercise some of that. You'll be surprised by, for these non-technical people, honestly, you will be very surprised by how much that improves what you're doing if you break it down into multiple steps.
By the way, one thing I've noticed, one thing that can help you do that is the LLM. Just ask the LLM, hey, if I can break down this thing into a series of prompts, it would gladly spit out like an answer that you can then revise and iterate over to say like, hey, how can I modularize this complex problem that I'm trying to take on? So it's easier. One, it's easier to sort of get a handle on all the different steps, and then easier to sort of optimize. And then decide which sort of fine-tuning method sort of works for you better based on the amount of data you think you can collect and the amount of dollars you're willing to spend on trying to do this.
And
any last thoughts, Alex, before we wrap up? I think hopefully people found discussion informative. But one thing we always ask is like, hey, put your comments. We love your comments. We've been reading it. Keep them coming. Also, let us know if there's other topics that you would like us to discuss in future episodes. Please also let us know that. But yeah, any last thoughts before we wrap up?
I think that this space is there's so much going on, and there's so much effort being put into research for it. Definitely don't be too concerned about going to the thing like, oh, I need to use the latest thing, because you know what. Everything was groundbreaking with LLMs a year ago. So it's not trash just because it's a year old. If you are building something and you're like, oh, I don't have the expertise, or I don't have the time in order to use the newest thing, that's okay. You don't have to. Like the stuff that's a year old is still very good. So keep an eye on the research. That's it.
Well, with that, thanks a lot for everyone who's still made it this far. And, like I said, keep the comments coming, and we'll try to keep doing these episodes. And thanks for your support, everyone. Thank you once again. This is Gradient Descent and Vishnu and Alex signing off. Thank you, guys.
Bye.